All right, so um we're gonna get into micrometers, okay? So this chapter we have already done steel rules and then the diet calipers, the past 2 weeks. So up to now, tools like your steel rules and calipers, okay, help us get close to the accuracy, but micrometers are where measurement stops being close enough and starts being controlled, okay? Repeatable and of course defensible. Yeah. Um, we're like it's kind of like we move beyond the general purpose, measuring tools, and then we go into true precision instrument. Yeah, so the starting point of true precision instrument is your micrometers. All right. So micrometers are where measurement stops being close enough. Yeah, I already told you, and we use it to control and defense, our measurements. And it is also designed to measure very, very small dimensions, very small dimension with much higher precision. Okay, so that's our aim. Of course, then the counterpart of the steel rule or the caliber, measurement too. So we're typically working in thousands of an inch or hundreds of a millimeter, depending on the micrometer systems. That's a lot, by the way. Even though it looks like, nothing when you look at the instrument, it's nothing, but it can measure. So 1,000 that's a lot. That's a lot of precision right there. 1,000 of an inch or hundreds of a millimeter. Okay, so humans are really smart. Okay, so this level of precision matters, of course, in manufacturing and of course in inspection. Manufacturing and inspection go, side to side. So where parts must meet strict again tolerance. Yeah, GD&T, we're in GD&T class. So tolerance is really important. And of course, it is a part, if a part is out of tolerance, even slightly, it's gonna fail in assembly. It will fail to assembly. So it will also function incorrectly. Yeah. And of course, it's going to be rejected, entirely in the manufacturing process. So in this chapter, we're going to learn how micrometers work and how to read them correctly, and then how to avoid common measurement errors, and of course, how to report measurements with proper precision and of course, confidence. Okay. All right. So before we get into the chapter, let's talk about objectives. We're going to take a look at what you should be able to do by the end of this chapter. So first, okay, here, you will learn how to identify the major components, of a micrometer. So knowing the parts really matter because each one is going to play a role, in accuracy and of course in control. So next, we're going to talk about when a micrometer, okay, should should be used. So micrometers are not replacements for calipers or steel rules. They are tools for situations where higher precision is totally required. Yeah. So you will also learn how to um correctly read, okay, both inch, of course, and your metric, micrometers. This includes, of course, understanding the scales, reading them step by step, and reporting values properly, which student they don't really do. You need to actually do step by step, but you like to skip or do like whatever. If you do whatever, you're gonna get whatever. That's it. So, and of course, we're gonna spend time, determining precision. Of course, the discrimination, GPE, greatest possible error. When we say GPE, it is an error. It's something that can happen, wrong in your measurements. And we, of course, aim the worst, right? So the greatest possible error, and we call that GPE. Of course, we can go down half of the precision. So you aim a precision, but if you're sloppy, we can go all the way down to half of that precision. So you understand the limits of your measurement and of course just the number you read. So another major focus, of course, um, is avoiding. So here avoiding the common micrometer reading errors. I would say. So most mistakes they come from rushing. They come from sloppiness and carelessness. Of course, misalignment or improper force. And you do all the time. Putting more force than you're supposed to put. And of course, and not from the tool, itself. Finally, you're going to analyze the micrometer measurement data. And of course, you will use Excel, for data analysis. And of course, the Excel, of course, which is, how measurement data is often handled. We use Excel all the time in real manufacturing and inspection environments. Um, Even though I would like give you the real world, situation. Usually engineers do the Excel part, and of course the technicians do only data collections, Of course, automation makes things really easy because of the sensor, collecting the data and you don't have to really do it. Um, all right. So what exactly is a micrometer? So a micrometer is just an instrument. It's a measuring instrument. It's a precision measuring instrument, I would say. So it is a design, designed carefully to measure very, very small dimension, with a very high level of accuracy and control, So micrometers are most commonly used for external measurements like your outside diameter of a shaft, or a cylinder, or the thickness of a plate, or the width of a part. Of course, compared to steel rules in your dial calipers, your micrometers provide much, much higher resolution. So this means like they can reliably measure much smaller changes, in size. Okay, so because of this precision, micrometers are commonly used in machining, and then of course inspection, and of course in quality control, very, very important. Sometimes they use in sophisticated calibration, okay. Of course, places where parts must see strict tolerances, and we use the micrometers, to be able to come up with the accurate, measurement. Think of it like when tolerances are tight, and gassing is expensive, then you will use your micrometer. Micrometer is the tool you want to use. So micrometers trade range, for precision, of course, and that trade is exactly, what makes them very valuable as a measurement tool. All right, now let's take a look at an example of the micrometer and we can see the components. This is just an example. Micrometers are different. It's a different manufacturer made different micrometers. So now let's take a look at the main components of this instrument, which is your micrometer. We're going to start from the left, and we have the anvil. Yeah, the anvil is right here. This is the fixed measuring surface. Yeah, so when you look at it, it is right here. So this side doesn't move, yeah, in measurement procedure, of course. So it provides one of the two contact points, yeah. So this is the first contact, and that's the second contact. So one of the two contact points for the measurement, and the measuring surface is often carbide, yeah, carbide tipped to reduce the wear. So here is your little, yeah, measuring surface right there. Usually carbide, yeah, tip. It's just a element, yeah, that we use for the special instrument like this. And the opposite to your anvil is the spindle right there, yeah. The spindle, of course, is going to move toward away from the anvil as you turn that thimble, yeah. So your thimble is right here. See this one little thimble right there? So the distance between the anvil and the spindle is your actual measurement. Yeah. Then we'll look at the frame. So here is the frame. So that holds like everything together. Yeah, you need to hold. So it's designed to be rigid. Yeah. So it doesn't equal flex during your measurement. So any flex would definitely, like bring the error up. Yeah. So you're gonna notice a thermal protection cover, yeah, on the frame. So this is your thermal protection cover. Yeah, look at this. Yeah, see that this cover right there? All right, so this is, like uh there to reduce the effect of the heat, yeah, from your hand. Because your hand produces some heat, yeah. Human body has a really strict temperature range that we can handle and we metabolize, yeah. So we definitely generate heat, yeah, from our hands. So even small temperature changes can definitely affect your micrometer measurement. Yeah, so don't think like micrometer is nothing, just be careful in your love. So moving to the right, we will go to here, and that's your sleeve. So this is the stationary part of your scale. So you can see it's markings right there. So this is where the main measurement markings are located. Okay, main measurement. Then of course your thimble also has another markings. Yeah, see that lines. So this is your secondary scale, of course, and this is your primary scale. Yeah, so turning that thimble, of course, advances your spindle. Yeah, and right this spindle, this is connected by the way. So if you turn, this is going to move. So turning that thimble, okay, is going to advance that spindle in a very small control increment, yeah, going very little. So at the end of that ratchet stopper, so this is the brilliance, of the mechanical, engineers. They make these things, by the way, including the precision instrument like this. So this is critical. Of course, it applies a very consistent measuring force, yeah. So you don't squeeze the part and then get a false reading, yeah. So the clamp, of course, here is your little clamp right there. See that? So that clamp can be used to lock the spindle. Yeah, so we use this to lock the spindle in place. So once the measurement's been taken. And of course, the key spanner, the key spanner is going to be, here. And of course, that is used to zero the adjustment, yeah, during your calibration. Um, And of course, I already, show you the ratchet stopper, here. So this is very, very critical because it applies the consistent measuring force, yeah. So make sure you pay attention to all these, of course, component, yeah, in your micrometers. All right, when to use a micrometer? So when should you use this thing? Yeah. So micrometers we use them when tolerances are plus or minus, 1,000 of an inch. So this is what it can do. or of course tighter. Yeah. Um, so when requirements get that strict, like tools like steros or diet calipers, okay, or just calipers, they're no longer reliable. Yeah. So we use micrometers. So micrometers are especially useful when measuring diameters, yeah, your thicknesses or your wire sizes, really tiny stuff. So dimensions where small errors can cause a very huge problem, in fit. Of course, a fit or function, we use the micrometers, not the stereo and not the dial calipers. So another key reason to use a micrometer is when high repeatability is required. We use micrometers, yeah. So this means that that multiple measurement of the same part, okay, um, should give you the same result, yeah, within the limits of that instrument. Of course, it's also very important to understand that micrometers are not general purpose tools. Yeah, they're not meant to replace steel. They're not meant to replace calipers. Yeah, so in industry, we use you have to use the correct tool. So choices matter. Yeah, so using the wrong tool is no good. Even if your number looks reasonable, it is better don't use the wrong tool. Yeah, because that can lead to rejected parts, and we don't want rejected parts in manufacturing. Yeah, we don't want rework. We don't want failed inspection. Okay, we want everything flow. Yeah. Of course, the precision tools are used only when precision is actually required. Yeah, so don't use a precision tool for the daily stuff. Yeah. All right. So now let's talk about micrometer measurement range. Okay, G&D range is really important. So unlike calipers, micrometers do not have a wide measuring range. So each micrometer is it is designed to measure, only a small span of sizes. So a typical inch micrometer measures from 0 to 1 inch. A typical metric micrometer measures from 0 to 25 millimeters. Okay, so that means you must always select the correct size micrometer. So before taking a measurement, so if the part is outside the tool's range, the measurement will either be impossible or unreliable. Yeah, so this also means a micrometer should never read, okay? It should never read exactly its maximum value. So if you ever get a reading like 1000 inches, on a 0 to 1 inch micrometer. So let's say, like this. So something is wrong, yeah? Either the part is too large or the tool is misused. Or the micrometer is auto calibration, one of the other things. So in practice, micrometers, like trade measuring range for precision. So be very, like careful about that. So that trade is again intentional, yeah, and it is what makes them reliable when used correctly. Yeah. All right. So let's summarize the major components of micrometer here on this slide. And of course, we're going to clearly define what each one does. So the frame is the rigid body, yeah, of that instrument. And of course, its job is to hold everything in alignment. So if the frame fixes accuracy, you're gonna lose it, yeah. The anvil. So the anvil is a fixed measuring face. So this surface does not move. Okay, it provides one side of the measurement reference. That's all it does. The spindle. So if you think about the spindle is a movable measuring face, yeah? And we know that we already look at it. So as the spindle advances or retracts, you're going forward and backwards. So it changes the distance between the spindle and the anvil, yeah? So that distance is really important. So that distance is your measurement. So the sleeve, yeah, so your sleeve is sometimes called a barrel, And of course, it contains the main scale. We already look at it. And of course, the scale provides the primary measurement reading. Yeah. And the next is your thimble. So your thimble is a rotating scale, yeah? And of course, turning the thimble is going to move the spindle in very small increment, yeah? So it is control increment. And it's going to allow you to read fine divisions, yeah? Little markings right there. And the end one, so which is the ratchet, yeah? And your friction thimble is very important, yeah? Critical. So it ensures a consistent measuring force. Yeah, we don't want to force it so hard. So this prevents over tightening. And of course, it's going to protect accuracy. Yeah, over tightening is no good. So make sure you avoid that. And the ratchet is not optional. It is there, okay, for a reason. So the lock, okay, is gonna allow you to hold a measurement in place, so it can be read or recorded without changing, okay? And then we will go into a vernier scale. So some micrometers also include another third, all right, the third scale. It is called the vernier scale, so which allows for even finer resolution, yeah? More than two scales, so that's a really good resolution, depending on the model, yeah, the manufacturer, of course. So every component has a job, okay? And understanding these parts is essential to using a micrometer very correctly and of course confidently. Okay. All right, so now let's look at a labeled micrometer. Yeah, this is a real world. Instead of a diagram, is a real world a micrometer. Yeah, it is little blue color. Yeah, it's kind of cute right here. And of course, we're gonna connect the names to the actual parts. So you'll be holding in your hands in the lab. Yeah, in the lab day, of course, starting on the left, this is the anvil. So here we can see the anvil. So the anvil is a fixed measuring face. It does not move. Okay, it provides one side of the measurement reference. Okay, so that's your anvil. Then we're gonna look at the spindle. So the opposite of the anvil is your spindle. So the spindle is movable measuring face. So as the spindle moves forward or away from the anvil, the distance between these two faces, they change. Okay. Of course, that distance is what we are measuring. Yeah, so these are measuring faces together, the anvil, spindle from the measuring faces like that. Yeah, so these are the only surfaces that should contact the part being measured. Yeah, we're gonna put the part right in here like that. All right, the large curved body is your frame, yeah, which is this guy right here. Okay, so the frame holds everything. I already told you about this in alignment. Of course, it must remain rigid to maintain the accuracy. Yeah, of course, you also have a thermal protection right here. Of course, the rotating portion is your thimble right there. Yeah. Um, so here, the stationary portion is this little sleeve right here. See, like sleeve with the vernier graduation. So we have like a two, yeah? Instead of one sleeve scale, we have a two scales right in there. Yeah, see this very carefully. So on some micrometer, the sleeve also includes the vernier graduations, and it's definitely give you the higher resolution readings. Yeah. So the rotating portion is your thimble. If you turn the thimble, it advances the spindle, okay? And of course, it's in very small control steps, yeah, like that. And this is how we achieve the precision, okay? So all is a mechanically engineered product, yeah? Of course, at the end of the micrometer, you're going to see the ratchet stop. Yeah, so this is extremely important because it applies a consistent, yeah, measuring force. So when the ratchet clicks, you're going to stop turning. And of course, the more force doesn't mean a better measurement. Yeah, you must control your force. All right, and finally, the spindle lock. Yeah, so your spindle lock is this little thing right here on the side. This allows you to hold the measurement in place, of course, so it can be read or recorded without changing. Yeah. So as you use the micrometers in your lab, you have to always think in terms of these parts and then their roles. Yeah. Um, so make sure you read before you come to lab. And of course, accuracy comes from understanding both the tool, yeah, the parts, and of course the measuring process. Yeah. All right, now let's talk about why measuring force matters when we use, okay, the micrometer. So one of the most common causes of micrometer error, yeah, if you make mistakes, so it's over tightening. You don't want force, okay? Applying too much force, it can compress the part, so be careful. Uh, flex the frame, we don't want that. Force the spindle, yeah, farther than it should go, it's gonna just break, okay? So all of that leads to the incorrect measurement, so please avoid them. And this is what micrometers are like, equipped with a ratchet stop because the ratchet is designed to apply a consistent, measuring force every time you use it. So when the ratchet clicks, that's a warning and you have to stop, and that is your signal to stop turning. Yeah. More force doesn't mean a better or more accurate measurement. In fact, it usually means the opposite. Yeah, it's no good. All right, so in precision measurement, consistency matters more than everything, more than your strength. Yeah. So two people using the same micrometer with proper technique should get nearly the same reading. Yeah. So this is where human error often happen. So your micrometer itself is precise, but the user, of course, is usually the weak, link. Using a ratchet correctly removes that variable, of course, and also protects the accuracy. Okay, so just be careful. All right, so on this slide, we're looking at a dimension, micrometer drawing diagram, of course. So the first is a little bit different micrometer, yeah. Well, I'm just giving you like different micrometers so you're aware of it. And oh, sorry, I hit it. All right, where was I? Okay, so this is just a different micrometer, yeah. And the first thing I want you to notice is the unit system, yeah, written right here on the side. So all of the dimensions shown here are in millimeters. Yeah, look at this. So that means that you're in metric, yeah. So as indicated on the right side of this slide, so that means that every value on this drawing is a metric dimension. Yeah, so make sure you understand that. Of course, in the lab, make sure you look at your micrometer, yeah, and understand which one is an inch and which one is a metric. So this drawing shows the physical size and of course the geometry of a micrometer instrument, not a measurement taken with a micrometer, yeah. So in other words, we're looking at the tool itself as a engineered object here, yeah. So the dimension label here, such as your frame size, yeah, look at that. Okay. Um, your spindle length. Yeah, so look at this. And of course, see this, all of this. Each one of them is dimension. Yeah, just showing you, the size of a micrometer here. So the dimensions are labeled here, all of them, yeah, overall length, of course, exists to define how the micrometer is manufactured, how it fits within the intended measurement range, just trying to give you the size of it and how everything is, dimension so you can be able to understand how we manufacture a micrometer. Yeah. So this reinforces an important idea. Micrometers are designed for a specific range and a unit system. Yeah. A metric micrometer is built like this and scaled like this, and of course calibrated differently than an inch micrometer. Like they're different. Of course, when you use a micrometer, you're not just reading numbers, you are working within a system. Yeah, so remember that. Of course, that includes the tools, geometry like this. Yeah, its scale and its intended range. Yeah. So as we move forward, we're going to focus less on the physical dimensions of the tool and more on how to read the measurement skills accuracy. But this slide is going to help you. I'm just giving you a little extra, yeah, to help you understand that precision starts with the design. Yeah, we always draw something like this to be able to build sophisticated, yeah, measuring instrument like this. All right. Excellent. So now we are here. So now let's connect these very important ideas. Yeah, your precision, your discrimination, your greatest possible error. We call this GPE, of course. In here, we're dealing with inch, okay? Inch micrometer. So starting with the sleeve, each major division, start with the sleeve. And then, of course, each major division on the sleeve, represents standard is 0.025 inches, yeah? And of course, this comes from the screw thread design of that micrometer. Then we go into thimble, thimble reading. So thimble is divided into thousand of an inch. So each thimble division is gonna go like 0.001, okay, inches. So here is, see, like start from here and here start at the end, yeah. So this is the smallest increment you can directly read on a standard inch micrometer, yeah. So some micrometers, they also have like a vernier, another scale near increment, because this can go all the way to the number four. See the fourth decimal, 0.0001 inches in accuracy. Yeah, so pretty good. All right, for a typical inch micrometer, the precision is 0.001. Yeah, typically this. Of course, because that is the smallest normal readable, increment. The greatest possible error, you divide that, okay, by 2, so half of that smallest readable increment. So since the precision here is about 0.001, your GPE divide that, okay, by 2, you're gonna get, of course, this, which is 0.0005, yeah? Of course, we put it in a good format like this, a plus minus range, and then the unit, yeah? So we know that which type of micrometer we are dealing with. We are in inch, okay, micrometer. All right. So the GPE is not a guess. Yeah, we calculated, and it is defined limit based on the instrument design. So every reported measurement should be understood, yeah, within this uncertainty. Okay, you're looking at actually this is error, okay, and this is precision. Precision is this, error is half, since because you do the error, your precision is not only half good, okay? So when you report a micrometer measurement, you're reporting a value. So you have a measurement value, and then of course you have to definitely give this, yeah, acknowledging this precision and of course possible error that can happen when you measure, yeah? All right, now let's look at precision discrimination and greatest possible error for metric. Yeah, so metric micrometer. The same, of course, it's just a different, scale. So on a metric micrometer, your sleeve increment is now 0.5 millimeters. Of course, each major marking, on the sleeve represents half a millimeter. Yeah, so the thimble increment is 0.01 millimeters. So it means that each division on that thimble adds 1,000. Yeah, this is 1,000. Sorry, adds not 1,000. Actually, this is only two. So 100. Yeah, 100 of a millimeters to the reading. Yeah, we have only two decimal. I misread it. Okay, so because you have like a 0.01 millimeters. Yeah, that is the smallest directly readable increment. So the typical precision of a metric micrometer is 0.01 millimeters. Yeah. Then of course we're gonna to divide that with 2, so you get greatest possible error, GPE, is always half of the smallest, okay, readable increment. So for a metric, okay, micrometer, your GPE is plus or minus 0.005 because we divide this by 2, and then of course we're going to give the correct unit millimeters. Yeah. So just like which inch micrometers, this error is not random or optional. It is defined by the design of the instrument. Okay, so metric micrometers are often cleaner mathematically, but many errors still come from misreading. Yeah, misreading the half millimeter marks on the sleeve. Yeah, this little thing is give you trouble. I don't know why. Yeah. Um, there's a funny thing, in the lab or in the shop floor. They always think like micrometer is easy. Yeah, I mean, metric micrometer is easy to read, and that's why they make a lot of mistake on the sleeve reading. Okay, I don't know why. Um, of course, so pay attention, yeah, to those marks. These marks are pretty critical. Don't think like it's easy to read, but it isn't. So when you report a metric micrometer measurement, you are reporting, both the value and its uncertainty. So you have your measurement value, and then of course we are going to give this uncertainty, yeah, because you can make errors, and that error can go about this much, yeah. So that's the greatest you can go, by the way. So precision, of course, error, they have to always go together, yeah, in your report. Right, next slide. Now let's break down how to read the micrometer scales. I give you a big diagram here, so you can see clearly. Yeah, starting with what you see here. Yeah, sleeve scale right there. So focus on the sleeve scale. So this is the main, your stationary scale. Yeah, on the body of your micrometer. So you always read the sleeve first. So whatever value is, like fully visible on the sleeve is your starting point. Okay. Uh, so when you look at it, see, this is fully visible. So you're going to cut it, okay, right there. So now you're going to look at, don't worry about this little gap. That gap is taken care of by this and this, okay? So now look at the thimble scale. So the thimble scale rotates, yeah? So its markings are here, yeah? So the markings align with a reference line on the sleeve. So when you see this, that's your reference line right there, yeah? And the markings are going to align with that, okay? So pay attention to that. So the thimble rotates, markings are aligned with the reference line on the sleeve, and each division on the thimble is going to represent a small increment. So this is where you add precision to the sleeve reading. Yeah, so all the instruments are pretty the same. So you're gonna add this and that all together. Yeah, and now it is showing, of course, right here. Yeah, look at this. Yeah, so it's already at the when you look at it, it's your 25 is here, yeah, 24 is here. Of course, we're just gonna take it like 23-ish, okay, here. So that's already there, and of course this is not yet. So that will be taken care of by there, yeah, by the other scale right there. So we will cut it right here at 23, okay? Um of course, if your micrometer has the third scale, which is your vernier scale, so it's going to allow you to read even finer detail. So the vernier scale works by lining up one vernier mark exactly with the thimble mark. So only one line will line up perfectly in the instrument. Yeah, we make it that way. So this is a vernier value you add first. So here you pay attention. Yeah, none of them line up. And this is the only one that line up. So here, yeah, this is going to be your fourth decimal. Yeah, look at that. Yeah, this is your third, of course, and the second. And of course, so here is your third and second sometimes. So you add them up. All right. So make sure like do not jump around between scale. Don't do that. You're gonna start with sleeve and then thimble and then vernier last. Yeah. So don't jump around. And don't guess. Every number you record got to come from a very clear aligned marking. Yeah. Like this, like that, and like this. Okay. So as we move into the example, you're going to see the micrometer reading is not difficult, but it does require patience, order, and of course, attention to your alignment. Yeah. Okay, so here you have two, yeah, a point 0.5. This one didn't pass. And then of course your thimble is definitely 0.23. Your vernier is 0.001. Okay, so we're just following the standard, yeah, which is this. Um, for this, of course, metric, yeah, metric, metric scale. So you get 2.731 millimeters, you know, for this reading. Okay. All right, now let's get into absolute versus comparative measurement. So now let's clarify an important concept here. So absolute, yeah, and then of course comparative measurement. So micrometer give absolute reading, okay? Um, this means the measurement you obtain is a direct numerical value taken from the scales on that tool itself. Okay, so that's what we're talking about. So when using a micrometer, you're not zeroing the instrument against the part. You're actually reading the position of that spindle, yeah, relative to the anvil, of course, your two surfaces, yeah, using the sleeve thimble and of course your vernier scale if one is present on that instrument. Okay, so the reading comes directly from the scale, not from comparison to a master part or reference block during the measurement. Yeah, come right from that instrument. So this is different from comparative measurement. So comparative measurement is like your diet indicators, yeah, or comparators. So these are the instruments that we use as a comparative instrument. So where the two is first zero against a known reference, and then of course you use the measure deviation, yeah, from that reference. So for micrometer, you're reading the tool itself. So that's why it's powerful. So that's why proper calibration, correct zero settings, correct reading techniques are very, very critical. Yes, understanding this difference gonna help you choose the right instrument and of course interpret the measurements correctly, yeah, in manufacturing and of course quality control, yeah. All right, let's see how to read. So reading an inch micrometer, yeah, we will take a look at the steps. So first you're gonna read the upper sleeve scale. Yeah, so this gives you the number of full tenths of an inch that are visible. So only count markings that are completely exposed is your very first rule. And then of course you read the lower sleeve. Yeah, lower sleeve scale. Each of these markings is always about like 0.025 inches. So if a lower sleeve mark is visible past the reference line, it must be included in the reading. Yeah. So anything that don't pass, don't include. So after that, read the thimble scale. So each division on the thimble scale is going to represent 0.001 by standard, yeah, inches. So find that number that lines up exactly with the reference line on the sleeve. And of course, you're going to add that to your total. And then micrometer includes if your micrometer has a vernier scale, then read that. The vernier is going to allow you to add an additional 0.0001, yeah, inches. So sometimes it's kind of like a 0.001 like that. So it also depends on, yeah, depends on the instrument, right? So we did the metric, yeah, metric micrometer, and vernier has like a 0.001. For inches, you have 0.0001 inches, yeah, like where is it like this? Of course, but only if vernier line, okay, aligns perfectly, you have to count that. So finally, add all of the values all together, like we always do. So every correct micrometer reading is the sum of the sleeve thimble and the vernier values. Yeah, so most incorrect answers happen because one of these steps is skipped. So if you follow this order every time, you're not going to have any kind of issue. Yeah, so micrometer readings become predictable, of course, also reliable. Yeah. So this is your inch micrometer reading example. So let's say upper sleeve, we get like 0.200 inch, okay? Lower scale, we get 0.025 inches, okay? This means like the last fully visible tan on the sleeve is this, okay? If you have to explain it, it is really hard, but that's what you see. Just read the one that you see, okay? Marking. So that's how I take it. Um, if it's exposed, then read it. If it's not, don't do it. Okay, so here is the one lower sleeve line is visible past the reference line, so we take it. Of course, each lower line is 0.025, yeah. Then thimble, of course, in this example, we get 0.018 from reading. So the thimble line, a line, yeah, with a reference line is actually 18. That's why we get 0.018, yeah. So each division is 0.001 inches. So 18 divisions will give you 0.018 inches, yeah. Of course, the vernier has like a 0.0007 inches. So the seventh vernier line aligns, okay, exactly with a thimble scale. So each vernier division is 0.0001 inches in inch micrometer. Seven of them is going to give you 0.0007 inches. So now you're going to add the whole thing up and you end up getting 0.2437. And then we're going to throw in, okay, our GPE. Okay, so GPE is 0.00005 for this micrometer because the precision is 0.0001, yeah, which is your vernier scale right there. One unit of the vernier scale is the smallest one that micrometer can be able to handle. So your reading is 0.2437 plus or minus 0.00005 inches for this example. Okay. All right, so this diagram is showing you how an inch micrometer actually works mechanically. And of course, this is what prevents a reading error if you understand it, how you should be reading it. So when you rotate the thimble, yeah, when you rotate the thimble here, the spindle is going to move linearly in and out. Yeah, spindle movement is controlled by the thimble, turning the thimble. So the motion is controlled by a precision screw. Yeah, thread. The precision screw thread is mechanically is a goal. Yeah, because of that, you can be able to read these fine, okay, I would say markings. Yeah, like that. So the screw thread inside the barrel, okay, is really important, part for the instrument to be valuable. So one full revolution of your thimble, okay, is going to move the spindle 0.025 exact inches. Yeah, so that's why the lower sleeve scale is marked 0.025 inches increment. Okay, is right here. Yeah. So when you look at this, and that's like a quarter. Yeah. So 0.025 definitely. See, one, two, three. So you have a one, two, three, four, quarters right there. So that's a zero point 0.5 and that's a point, 0.025. Of course, this is a 0.05 and this is going to be another, 0.075 is right there. And then of course, 1 inch is here, for you. Um, so every four full revolution of your thimble is gonna move the spindle 0.1 inch. Okay, so now this is 0.1 inch. See, like how fine the instrument is. So which correspond to one major division on the upper scale sleeve. Do not think like that's okay. That is the increment. Actually, where increment is gone this way. Okay, these are just showing you how many parts are there in one increment, okay, which is equivalent to the one revolution of your thimble. So it rolls one time, two times, three times, four times, and you got 0.1 inch, yeah, on this scale. All right, all right. Uh, so if I say like 0 to 1, how many revolutions of the thimble? You have to say four of them in there. Yeah, four of them in there. Don't give like this is one turn. It isn't. Yeah, we turn four times to get to 0.1 inch. So that's really fine. Yeah, a fine motion that we're doing. All right, the index line on the sleeve is your reference point. Okay, so here's your index line. See that? That is the reference point. Okay, reference point for what? So reference point for this. Okay, so all readings are taken where the thimble graduation aligns with that line. So here, our reference line is right here, and we are going to read right here. Yeah, so the thimble graduation divide each you have about 0.025 inch, okay, in this example revolution. So you have about 25, yeah, so 0, and then here 20, so the whole round is 25 parts you have. Okay, so little markings right there go 25 of them. So it gives you about 0.01 inch per division. So time 25 is going to give you 0.025, yeah? So as the thimble rotates and moves along the barrel, the reading you see in the combination of how far the spindle has advanced and how finely that motion is subdivided. So micrometer is engineering, okay, genius, all right? So we made this way because your turn is incredibly small, and it is going increment of 0.1 inch. Increments of here, okay, 0.001 inch going, okay? If you got like a vernier, that goes like even 0.0001 inch. Okay, so even finer. So as the thimble rotates, moves along the barrel, the reading you see is a combination of how far that spindle has advanced and how finely that motion is subdivided. Okay, so that's the whole mechanism of micrometers. So in other words, your micrometer is converting rotational motion into precision linear distance. So, and every scale you read represent a physical movement of that spindle. Okay, so right over here, you can see it. Of course, it definitely not a guess. Yeah, don't do that. So make sure you read correctly in the lab. All right, next, what do we have here? So now let's go through how to read a metric micrometer, and I want you to notice that the logic is simpler, yeah, than inch micrometers, but mistakes are still very, very common. So first, read the sleeve, okay, in millimeters. Count the whole millimeters marks that are completely visible to the left of your thimble, yeah. Everything that is not visible, please don't do it. Even if a little gap is there, you won't count it. Only the visible marking you're going to count. So that's going to give you your base measurement. Of course, next, this is the step students miss most often. You have to check for the half millimeter mark. Yeah. So if the 0.5 millimeter line is visible, you must add 0.5 millimeters to your reading. And if it isn't visible, you do not add it. Yeah, we go by 0.5. So there is no guessing right there. So after that, you're going to read the thimble scale. So each division on the thimble scale is going to, okay, each division on the thimble scale is going to represent 0.01 millimeters. So that is like 100, yeah, of a millimeter. So find the thimble number that lines up with the reference line, and then you're going to add that, okay, to your total. Yeah. So that's basically what we're doing in micrometer readings. So finally, you're gonna add everything together like we always do. Your whole millimeters, your half a millimeter, yeah, if present, and then of course, you're gonna add your thimble reading to it. So metric micrometers are very clean mathematically, but most errors come from ignoring or misreading the half millimeter mark. Yeah. So train your eyes to look for it every single time. Yeah. All right, here's an example for metric micrometer reading and adding. So first we have a sleeve and we read it like a 7.0 millimeter. So half millimeter is visible, so that's a 0.5 millimeters. And of course, your thimble is 0.32 millimeters. So we're gonna add them up, 7, and then of course zero point 0.5, and then we have 0.35, altogether 7.82. Yeah, here. Okay, so 7.82. So that is going to give you, yeah, 7.82 millimeter plus or minus 0.005 millimeter is your GPE because all precision is 0.01 for that instrument. Yeah. All right. So that's how we read the metric. micrometer. All right, let's see with this little diagram here, you can see, yeah, your sleeve and of course a 23, yeah, we have 20, and then of course one here, two here, and then of course three right there, very visible. So you have 23 whole millimeters, yeah, they are visible. So we're gonna multiply that, yeah. So the 0.5 millimeter mark is not visible. So when you take a look at it, half of them is going to be 0.5, yeah? So that's definitely is not visible. So you only have like a 23 millimeter. So do not add 0.5, yeah? Because 0.5 will come like here, see, one, two, three, four, five. So you're gonna go one, two, and half of that, yeah, is going to be 0.05. So altogether, when you carefully look at it, yeah, we don't see the point five. Yeah, point five isn't there. So point five line is right above that. Yeah. So we have like a one, two, three. So look at this. Half is that. Half between that two is here. And then of course we can see this line right here. Yeah, it's completely uncovered. It is completely covered by this line. Yeah. So therefore no half millimeters graduation visible or uncovered. Therefore, we don't count. So we have only 23.0 millimeters for the first scale. Then we move on to thimble. So when you look at the thimble, you have 15, yeah, graduation, and that is aligned with your reference line, yeah. So therefore, you have 15 times 0.01 for each unit, little tiny one right there. So 15 times 0.01 is 0.15, yeah. So you get 0.15. So add them up. So altogether 23 plus 0.15, you're going to get 23.15 for this reading. Okay. So the reading is 23.15. Your GPE is 0.005 millimeters coming from 0.01 millimeters precision. Yeah. And put them, of course, in the right format with the range. All right. So common micrometer reading errors you need to know. Yeah. Um, All right, so the rules are reading whole inches instead of 10. Don't do that. Using the wrong sleeve line. Okay, that's wrong. Forgetting the 0.025 in inches increment, you always have to look for the smallest one. Misreading the vernier direction. Make sure you look for the line, yeah, properly aligned vernier marking. Missing or incorrect units, okay, for your reporting. Yeah, don't do that. All right, now uh we're gonna look at micrometers and the gauge blocks. So gauge blocks are, we use to verify the micrometer accuracy. So that just we're just trying to connect the micrometers with the gauge blocks. Yeah, micrometers don't exist in isolation. Of course, in metrology, yeah, every measurement tool needs a reference, and that reference is the gauge block. So your gauge blocks are used first to verify the micrometer accuracy. Yeah, before trusting a reading, we check the micrometer against a known certified length, and that's your gauge block. So if your micrometer doesn't agree with the block, then the micrometer is the problem, not the part. So we have to pay attention, yeah, to that. Um, so they're also used to practice, yeah, correct technique because this is where students learn proper feel alignment, yeah, use of the ratchets. The micrometer can be perfectly calibrated, and of course, it's going to still give bad readings if the user rushes or over tighten the instrument. So finally, gauge blocks allow self-calibration checks, yeah. You're not performing a full laboratory calibration, but you are confirming that the tool is still reading correctly, within its expected accuracy. So this is why we say metrology is a system, not just a collection of tools. And of course, your micrometer is going to give the reading, but the gauge block is going to give the micrometer credibility. Okay. All right. So what are we gonna do with the Excel? We're gonna use Excel to calculate. Yeah. We are going to do a data analysis by using Excel, and we're gonna find the mean is your average, your minimum, maximum. Yeah. Of course, review your Excel. Yes. Formula. I don't know. Some of you have, I think, already taken the computer application, which you learn Excel how to use it. If you haven't done it, so just make sure you do that. Of course, how to use the formula to get range in Excel, you need it, and the simple standard deviation, of course. That's a pretty standard Excel formulas that you need to use to analyze the data you get. Yeah. All right. This is just wrapping up the chapter. So micrometer, like it gives us the highest precision, highest precision of any common hand tool. Your stereo, your dead calipers, and your micrometers are called common hand tools in the lab, yeah. But that precision only matters if we use a tool correctly. So you have to use micrometer correctly. And your micrometer itself is, capable of excellent accuracy. So your errors come from the person holding it and using it and measuring it. Yeah. So be careful in the lab. So you have seen that micrometers use multiple scale, your sleeve and then thimble, and then of course a vernier. Yeah. So the sleeve, the thimble, sometimes the vernier all contribute to your final reading. We have to add them up. Yeah. So if you miss even one of them, the measurement is wrong. So there's no, of course, a partial credit in industry. The number is either correct or it isn't. Your mathematics, okay, adding and your calculation, yeah, multiplying the smallest increment with the amount of markings you counted. Yeah, make sure you do that. Don't get all the decimals wrong. Yeah. So measuring force also matter. Don't force it so hard. Yeah. So guys always force really, really hard. You don't do that. Be gentle. So that's why we use a ratchet stop is to check your force. Yeah. So the consistent force is going to give you the consistent results. So strong hands don't improve the measurements. Controlled, technique is very important. So make sure you use ratchets and listen to the click. So units are always required. A number without unit is meaningless. So inches and millimeters are not interchangeable. And of course, mixing them up is your greatest error. Yeah. Of course, we also use the gauge blocks to verify the accuracy. So they're not optional accessories. They're like how we confirm the micrometer is telling the truth. Yeah, we gauge it. Of course, finally, your measurement doesn't stop at reading the tool. Yeah, so your measurement, they're like how we confirm the micrometer is telling the truth. Okay. Um, so, I would say like your Excel, like when you get to the Excel data analysis, um, you have to look at the averages or the ranges or the variation. Yeah, there's standard error, of course, deviation, standard deviations. Yeah, and of course, because that's what industry expects the interpretation, not just your numbers. Yeah, so you have to put meaning to your reading. So what's going on with it? So this chapter sets the standard for seriousness in your measurement. So sloppy habits, you have to end it. Yeah. But this is just your homework reminder. I put it there so that way you kind of so you do your exercise 1, 2, 3, 4, 5 in your textbook, yeah, covering your inch micrometer reading, of course, inch micrometer with vernier, and then metric micrometer reading, and then unit conversion, and then of course we touch up a little bit of the percent difference, yeah, review. And of course, here is your source. Identify where the materials come from. So that's the end of your chapter. What was it? Like chapter three, yes? Micrometers. So I'm gonna go ahead and stop right here.